update the slides that are available online for you. And also, you don't really need to read chapter 12 anymore. It's chapter 12 is sort of a copy of chapter 11 with some things changed, so it's a bit redundant. But anyway, last time we learned about Gore, and we said that it has a 17 residue window, and it uses this naive Bayes-like assumption that pairwise combinations of residues don't matter. It's only single residue positions that matter, and we talked about the pros and cons of this assumption. And then but there's another assumption which we didn't really give so much emphasis to, and that was that it only looks at 17 residues in a window centered around the sequence. Is that a problem? I think it's a good thing. I think it's not a good assumption. Can we really predict secondary structure from looking at 17 residues? No. What?
Basically, it's when we're talking about the 3D confirmation, we know that it's not necessary that certain residues are in contact with the residues.
Exactly. I mean, there are other residues around it that are stabilizing or destabilizing one or another of these secondary structure possibilities, right? And so you can have exactly the same sequence, but in a different protein, they'll fold into different secondary structures. Yeah, so context definitely matters. You can have a perfect information, every sequence of every protein crystallized, and train a 17 residue predictor, and it wouldn't get it right every time. Yeah, and so we're going to talk about how we can get over this assumption. Yeah, and so that makes two assumptions that Gore has that weaken it. It uses only local sequence information, and it doesn't consider pairwise dependencies even within the 17 residues. So there's a program called Predator that tries to address some of these. And it's based on this idea that if you have, for example, an alpha helix, you would expect some interaction between residues I and I plus 4. And likewise, if you have a beta sheet, then you have some pairwise interaction across strands. And so it's basically a Gore with a few terms that don't look just like probability of x sub I given c sub k. It looks more like probability of x sub I comma x sub I plus 4 given c sub k, for instance. And other than that, you can still treat it as naive Bayes, except some of the terms have 2 inputs rather than 1. And then so that would be the case for this alpha 4 would be the case for again I plus 4 interactions, and then you treat these interactions across beta strands some other way, right? Okay, and so this claimed a slight increase in accuracy over Gore. So Gore reported 63%. These guys reported 68%. But I'm actually I put this on here, but I don't think that's a really good idea to look at these accuracies and think they're bounded very tightly, right? Because this is totally dependent on which data set you use to validate your method. This is later methods, so there are a lot more sequences. It's possible that you could have lower reported accuracy and still be better. And also depend on how you chose your test set. Make sure doesn't contain sequences that are too similar to the ones you used to train, things like that. And so there's one way in which we try to get the structural context Or one famous way to do it was to use a neural network that has a few hidden layers that do different things. And we've already seen this from Arne, but just as a quick recap, the input layer here is going to be maybe a 17 resolution window, so maybe 17 wide. Except it's actually the way it's encoded. You probably have one input, one of these nodes for each amino acid type, right? So let's say 17 resolution wide would be 20 nodes deep, right? So if it's alanine, then only alanine node 5 position, let's say 17. So that's what the input layer would look like. And then you have some hidden layers doing some calculations, and then multiple hidden layers, and finally an output layer, which would maybe be either alpha, beta, coil, or something else. And Gore, you could think of it as even as a kind of a neural network, except it has no hidden layer, it just has input layer, output layer. And it just gives you just work with linear sums of what's given to you at the input. So this famous method by Burkhard Rost called PhD uses neural networks, and what it's doing is that it has basically one little neural network. I don't know how to call it. Let's say the first half of this neural network, all it's doing is predicting secondary structure based again on this sequence window, and again 17 residue sequence window. And it should be a little bit better than Gore because it's got this hidden layer, which could, in principle, look at pairwise correlations and so on. But what really makes it, what supposedly that gives it its boost in performance, is that this is only the first step. What you're doing is you're generating a sequence of different secondary structures, and then you use that sequence to query the protein data bank, and you get all these structures that have this secondary structure, right? So let's say you have some sequence, and your first neural network says, oh, this looks to me like it could be coil, helix, coil, I don't know, beta sheet, another beta sheet, and so on. And then it goes and it searches the PDB, and it comes back with a whole bunch of sequences expressed as sequences of secondary structure, right? So I might say, oh, I found something that looked kind of like this, you know, it's maybe a little bit shifted, something like that, right? But it gets a whole bunch of these, right? And what it's doing is that it looks at the context, and it says things like, okay, let's say actually, let's change it. Let's say my predicted secondary structure has a coil in here, and so if it has a whole bunch of sequences that they all have something like this, like a beta sheet that's longer than my predicted one, then it might infer that this thing is wrong, right? And so what's really good at in this layer is that it's correcting the lengths of secondary structures that it finds, because these moving window methods have a serious problem with just getting length wrong. Like they'll insert coils in the middle of alpha helices, or they'll just make them too short or too long. So this gives a bit of an improvement in accuracy, but again, even Burkhard Rost, even in his own paper, acknowledges that this totally depends on how you do it, because he initially reports 72%, then somebody else publishes a paper and says, oh, I gathered these several independent test sets, and I got something on average more like 65%. And Burkhard says, well, okay, fine, depends on your data set, so somewhere in that range is probably right. Let's see. Oh, sorry, yes.
So where again do you get the other information from? So the other secondary structure?
So this is basically, it's like you're doing BLAST, except instead of using sequence of amino acids, you're using a sequence of secondary structures.
Okay.
So
and which database is that then?
So I don't know how they implemented it, but I would imagine you could query it. Actually I'm not sure if you can query the PDB directly with sequences of secondary structures, but But you either do it directly into PDB, or you would download the protein data bank files and parse them and make your own database. Yeah, that type of stuff. I will say that the PDB has some really nice, really nice libraries that you can import and let you query it in all sorts of ways. So my bet is that they actually have this already implemented. Okay, so other questions?
Just
Yes.
something about, so this is better because it even rectifies errors that could be there in your query sequence as well. Like you
Yes,
mentioned the
because
quality.
remember you personally didn't make this query sequence, right? You gave it amino acids, and then it says, okay, this is my initial guess at what the secondary structure is, and then upon comparing to lots of real structures, it starts to make small corrections like this. You know, and small is right, because think about this. Like, this is still very close to what we got with Gore. I mean, Gore reported like 63%. Other questions?
So just dim the light a little bit, maybe.
Yes, I can.
Yeah, it's a lot of reflection. I think much
How's
more
that?
now.
Okay. Okay. The video is on, right?
Yeah.
Okay. So if there are no more questions, then I'll continue. So again, we're going to treat trend member proteins in Gunnar von Heine's lecture. And now we're going to talk a bit about coiled coils. So, coiled coils are two alpha helices that coil around each other, right? And there's a very characteristic signature, and the way so the way it's formulated is that you choose some 7 residue fragment, and you give it letter names A, B, C, D, E, F, G, and what you'll notice is that A and D tend to be hydrophobic, and E and G tend to be charged. Can you see why this would be the case? Anyone tell me why it should be this way? Physically speaking?
Maybe the other ones that are on the inside, so maybe.
Yes, exactly. The ones on the inside are buried.
And those has to stick together.
Yeah, exactly. I'm actually not entirely sure if the charged ones are sticking together, like in other words, meaning or if they're just hydrophilic, because it's also like charged or hydrophilic, really. And if an engineer is making this protein, they'll specifically choose opposite charges. But I looked, and it's surprisingly hard to find any evidence that is actually opposite charges that are needed in the biological phase. I mean, there's plenty of examples of light charges attracting, right? Because they can be mediated by ion, for instance. Do all coiled coils obey this rule, this heptide rule? What do you guys think? Probably not. Why do you think no? Why? Because biology is contrary. Yes, it's not like a human engineer that does follow the standard practice all the time. Yes, no. So definitely. For example, I've worked on human growth hormone. There's a coiled coil in there. It's very important. It's close to the zinc binding site. It doesn't follow this rule, right? I mean, it's actually got polar residues buried in there, and these things are not charged. And but it stabilizes this coiled coil in a completely different way, right? It has one of these residues that starts going across to this third helix that's not even coiled with, and it's getting pulled by that. And, nature will find some other way to do it, which is why these signals are so noisy. But this is a pretty good general tendency, like, statistically speaking. And it turns out you can actually detect this with a relatively cheap experiment. You can do circumzacralism. We have a machine here. Just ask the Grasslund, and she'll probably help you with that. Okay. So there's a program called Coils. And what it does is it looks for things that look like they're following this 7 residue pattern, right? So it says, okay, look, you know, I'll sort of scan and I'll look for things that look like, what do we say, A and D are hydrophobic. So here's an I and an E. Doesn't seem to follow the pattern, right? Looks like there's a lot of charged ones. Let me just make sure. Yes, A and D is what we're looking for. L and S, L and L. So, you know, you know, some of these seem to follow the rule, others are not, right? And but anyway, it's looking for a sliding window of 7, 14, or 21 residues that are enriched in residues that are following this pattern, right? And it gets different performances depending on whether you use 7, 14, or 21. But yeah, there's this issue that is still it's effectively naive Bayes, and that doesn't look for any pairwise interactions or any pairwise correlations, right? So, do you think there should be some pairwise correlation in this case? So, I mean, for sure these guys thought so, and so there's this program called Pairs that now looks at, instead of just single residue propensities, it looks for propensities between neighboring residues and between, let's say, residues K and K plus 4, right? Because you expect some interaction between residue I and I plus 4. Right. And so other than that, it's naive Bayes because it doesn't look at all pairwise correlations. It looks at certain ones, and then the rest it just treats as using single residue propensities. So leucine zippers, how many of you have heard of leucine zippers?
In previous, they look at residues 1 to 4,
Yes.
but why those?
Well, because we're definitely looking at talking about alpha helices, right? And so so you'd expect that residues that are 4 residues apart would be close to each other, and so there should be some. They should have some interdependency, right? So I mean, for example, you would expect to find 2 lysines next to each other, and then they even look, like across here, there might be some additional incompatibilities even within hydrophobic. I don't know what they would be, but you would expect them, if they're close to each other physically, to have some correlation or some preference.
And then is it to both sides that they look?
Yes, they look on, well, I mean, you don't want to do double counting. So if you already check I and I plus 4, you're not going to go then to I plus 4 and check against I, right? So it looks like it's one way just because they're arranging it so that the second index is higher than the first. But yeah, they're trying to get I think they're trying to get most of the pairwise correlations along the whole that are close enough to affect that hydrophobic patch, right? So pairwise correlations probably between the 2 hydrophobics and maybe one hydrophobics and one polar. Okay. Yes.
Wouldn't it be better if you do it twice to see positionally and to see the propensity better? Like if you take an average, like from both directions, just to be sure.
I think that would just be double counting though.
Yeah, I mean, but if you divide it by 2 to make sure that you just have the same.
But if you're looking at the same sequence,
and like you better take the residues that are following that pattern from either direction.
understand the question.
No, I meant like it'd just be like double checking, right? If you were to double count it divided by 2.
Well, I mean, you check on your math, right? Because you should get the same number, right? You can do that. Okay, so how many people have, or are there any other questions? How many people have heard of leucine zippers? So let's say, what do you think leucine zippers are? Why do they call them zippers? What does leucine look like? Does anybody want to give me some like just plain English explanation of why they call them leucine zippers?
Because they're two units like this, and you have the leucines in the middle, so it looks like a.
So you think they're like interlocking?
Yeah.
So that was the explanation that I heard when I was a graduate student, that that you got leucine here. Remember, there's a beta carbon and then there's a gamma carbon, and it's branched at the gamma, and then there's this other helix, and it's got this beta carbon and then gamma, and it's branched here, and things like that. Is this the picture that you've been that you were taught as well? Yeah, that's the picture I was taught. Except it's wrong. It sounds very appealing, and I think people heard the word repeat, they thought valine, they knew the structure of valine, they thought, it must be doing that thing, right? But if you look at any of these leucine zippers in a PDB structure, they're actually doing something quite different. They're just doing this thing, like they're like, oh, I'm just gonna take a nap here and lie down. And this guy says, oh, that looks pretty comfortable actually. I think I'll take a nap right here, right? And so they're just trying to maximize their hydrophobic contact area. That's it. And I challenge you to find a PDB structure that actually looks like a zipper. You might. I mean, I haven't seen this published. I just looked it up one day and I thought, yeah, no, that's BS. Okay. Yeah. So actually, this structure is kind of more like one of that. Not really a zipper. Okay. So let's see. So, are any questions about that? Let's see. So, RNA secondary structure prediction. We're going to do this two different ways. We're going to do by M-fold, which is an energetic method, and we're going to do it by coevolutionary methods. And actually, coevolutionary methods are really good at predicting RNA secondary structure, at least helices. Because interactions between bases are very modular compared to interactions between amino acids, right? Amino acids, like the entropy is just everywhere, whereas in nucleic acids, especially in double helices, it's a very specific interaction, and it doesn't have kind of the same, at least not to the same extent, the propensity to shift out of that interaction and come back in. And then further, it has a much smaller alphabet, right? It's got 4 nucleic acid alphabet as opposed to 20 amino acid alphabet. And so both of these things together make the coevolutionary signal much stronger. And we're going to learn the simplest method for calculating coevolution. It's not the only method, but it's actually amazingly useful for many things. So I very much encourage you to learn it well. And then we'll go on to M-fold. Because, yeah, sometimes you're not going to have enough sequences to do an alignment. Yeah, and lastly, of course, if you have a close enough structural homologue, then of course, this homology model, that's ideal. That's the best, short of having an actual crystal. Okay, so as we've already said, in RNA, you can have helices, you can have these hairpin loops, you can have internal loop or bulge, you can have multi-way junctions, etc. So there's lots of things happening, we're mostly going to be focusing on how to predict these helices. And so mfold assumes dynamic programming. And so that assumes, dynamic programming assumes that we have a subproblem, right? That we can break one big problem into small problems and solve them separately. And so for instance, let's say we have two helices like this, and we want to predict this helix and that helix. Could I break that up into subproblems? Was that a yes or a no? Probably, yeah. You can just break it here, and if all it matters is local interactions, then yeah, you can break that into subproblems. There are cases where you cannot do that, right? So a pseudoknot is such a case. So a pseudoknot can look something like this, right? We have this thing kind of switches back on itself, makes a hairpin, but then this thing goes on and makes a hairpin with the loop, right? And so that's not something you can break into a subproblem, right? Because if you were to cut it here, then you'd have what would you have? You'd have something that's like this, and then you have something else that looks like this, right? And you could do this thing on it, but this interaction across here, you won't be able to get, right? So you can't do a subproblem with things that, there are some structures that can't be broken up into subproblems, and pseudoknots are an example. Yeah, so here's an illustration of a pseudoknot. And so a pseudoknot is a structure where you have these base pairing lines crossing, right? And so if I cut it here, then I'm breaking basically all the base pairs. If I cut it here, I'm losing 3 of the base pairs, and so on. So there's no place I can cut it to break this thing into subproblem. So that's a major limitation of any dynamic programming method, and in particular mfold. So what mfold is doing is it's using dynamic programming to find all of the base pairing configurations that are consistent with this subproblem approximation and computing their energies. And this is actually a really hard problem, and you can't really do this additively the way they do it here, because for one thing, entropy isn't additive, but it kind of works to some extent. The way it works is you give a certain number of bonus points every time you make a base pair, and then when you have consecutive base pairs, you can give some positive rewards for each consecutive pair of base pairs, right? Because they're stacking between base pairs. And then, depending on how big this loop is, you're going to have to pay an entropic penalty, right? Because anytime you have some freedom and you take it away, that has a free energy cost, right? And so what's more costly, closing a little loop or closing a big loop? What do you think?
A big one.
A big one. Why? Because more freedom, right? It has more degrees of freedom. I just added all the rotatable bonds, and that gives you, that tells you how much freedom it has, more or less. So yeah, so depending on how many bases are closed, then there's this loop closing penalty. And it turns out that's going to be kind of analogous to your insertion or deletion penalty that we had in pairwise sequence alignment. So what you're going to do, very much analogous to pairwise sequence alignment, is you're going to take your let's say your one strand that you're folding on itself, and you put the sequence along one axis and the same sequence along the other axis. You can confirm that this is GCAAA, this is GCAA, it's the same sequence. But and here, instead of aligning one sequence to another, you're kind of aligning the sequence to itself, right? In this reverse complement way, right? So for instance, let's say we focus on the 3' and the 5' end. We say, oh, this looks like the 5' G could base pair with the 3' C, right? And so we put a dot here, and that's GC. And actually you'll have different points depending on whether it's GC or AU or AT, or sorry, AU in this case. But anyway, so here we have GC, so we can give it some max score. And it turns out that there's another one right next to it, nice. And there's potentially one right here. Except here we have the situation where this U could also be base pair wins A. So either of those solutions could work. But to jump, let's say choose this one and then jump to here, that jump is effectively closing a loop, and so that has a penalty. So it's basically like it's very much like tracing through this alignment matrix, except now the actions have different. There are different actions. Like you just don't give them the same names. You don't give them exactly the same points. But other than that, they're quite similar. For instance, if you go from here to here, remember that if you have match here and you have match here, all you had to do when you did sequence alignment was add up these two match, or add a new match score to the already summed match score there, right? Here, when you go along the diagonal, you also get a stacking bonus, right? So the action of just going on to the next base pair would give you an additional benefit of that. And then like I say, if you go vertically or horizontally, then you're talking about potentially a loop closing penalty. And so they're different rules, but very similar process. So let's see. Let's see if I want to try to read this matrix and tell me what this secondary structure would look like. Anyone want to try it? You can try on your notebooks, and then you raise your hand if you think you've got it. Right back there?
You could basically fold it in the middle.
Do you want to just come up and draw your answer?
Sure.
Okay.
And then there would be two A summa which are not bound.
Mm-hmm.
And then so this could be like the wooden loop or whatever, but the rest could bind together. That's what we would do.
Let's see, so G is, so this G, C, A, C, G, and U, C, G. This G is that one. Wait, is that one? No, you're saying something else. Here, which A is this? You want to point to it? A, U,
This
C,
pairing,
okay.
then these two. And
but-
then there's
but-
just three A's for one U basically.
Because see, I'm reading A, U, C, G. So where's AUCG here? Oh, it's this. It went this way, like this.
I think
Okay.
Yes.
And then this is base pair with a C.
yeah, exactly.
Okay. Yep. I'm starting to follow you. Geez, and then there's a C, which is base with a G. That's this one. And then there's a G. Or, then you went back up like this.
No. This is a continuous sequence like that. We just basically fold it in the middle.
So where's the 5 prime end? Is it this? Here on your diagram here.
I don't know which one is which, but this one is one end and this one's the other end.
Can you point to the C there?
This one. Oh, that one.
Oh, yes. Okay. So this is the 3 prime. Okay.
And then this is the 5 prime end.
This is 5 prime. Okay. GCAA. Okay. Now I got you. Here, let me try to So basically 5 prime with the 3 prime, okay, like this. Okay. And that's definitely base paired with this guy.
Like either of these eight.
Either the A's, it could be potentially be this one.
Yeah.
Right? Okay, good. And then here is a C, and that's base paired with a G here. And the rest are not base paired, is that right? Like this is
I mean, I don't know how.
C, G, A, and then G, C. Yes, and then these guys, the rest are not. GCAA, GCG, and there's A, there's U, C, G, C, U. I think we got some kind of framework from here. 1, 2, 3, 4. Too much. Okay, I think that's what you're saying. Okay. Does that make sense to you people? Okay, so was Linda, right? Louisa, sorry. Okay, so Louisa is saying that this, I'm going to draw it a slightly different way, which is exactly equivalent. She's saying there's this is basically a 2 residue bulge. This. A, G, C. And then there's G, K, U, C, and then G, and then C, and U, and G, and C. Okay? that's exactly right. And yeah, and alternatively, you could do this. Okay, and so there are two solutions. Yeah, that's pretty much it. Okay. And if you ever run mfold, you'll see that the same sequence can give you this, this, and this. And you look at that and you think, well, thanks. I mean, frankly, I would just basically never trust mfold. I mean, I look at these papers where they say, oh, we ran mfold, we got this, and then we did the experiment and it confirmed it. I thought, okay, how many times people do that and not get it to match up? And then what happened? They just didn't publish, right? So it's almost like a coincidence that mfold happened to agree. I think, like, at least, that's my own personal prejudice, right? But anyway, I would just be very much like grain of salt with mfold. But anyway, it's very popular. I'm just trying to cover the most popular packages to some extent, and also it's because the concept is useful, but you just have to be skeptical, I think. And then we have any other questions about mfold? Okay, so then we have mutual information, and like I say, this is a really, really strong method for RNA. It's basically 90% of secondary structure predictions for RNA are done with mutual information, or some co-evolutionary calculation. But mutual information is the most elegant, and the one that's basically sprang full grown from the head of Claude Shannon, and just works for so many things. There's a lot of things for which it doesn't work, right? It's really crappy for trying to calculate coevolution in proteins. Like it's just the data is just too noisy for that. But anyway, for RNA it works really well. And so mutual information is basically trying to ask the question: are two positions evolving together, right? So if you see this thing in this sequence, and it's a G and a C, right? Then there's some other organism that says, okay, here has an A, right? What does this have to become to maintain that helix? Yeah, that's my study. Yeah, it has to be U, right? So if you see some sequence that has like G, C, and then like G, C, and then C, G, C, G, A, U, U, A, things like that. Where you see it change here, it very often results in a change here. Then you can say, oh, these two positions are co-evolving, right? So another way of saying that is that there's communication between each channel. This is one channel, this is another channel, right? So and these symbols, they can be basically anything, right? Is everything all right? Okay, so you can have one alphabet here, and you can have a completely different alphabet here, right? What you're effectively asking is whether there's a difference between the joint probability of x and y and the product of the two marginal probabilities p of x and p of y. And if they're basically the same, then they're not co-evolving, and to the extent that they're different, then they are co-evolving. Okay, and so here's the formula you can use. This is technically you can say this is the Kullback-Leibler divergence between p of x comma y and p of x times p of y. And so that's basically a measure of how different these two quantities are. This one versus this one. Okay, and so this was first used to predict the secondary structure of tRNA by Mike Levitt in 1969, and if I recall correctly, he had 14 sequences to work with. And he more or less got the secondary structure right. And 30 years later, Robin Guttel at the University of Texas did it again with 1,300 sequences. So guess how many more base pairs he found? If I want to guess. He found 1. So this is a really good method, even with quite limited sequence alignment, multiple sequence alignment. Okay, so let's just do an example. This one was in your quiz, so probably you know how to do it already. So does somebody want to try this one? Come up on the board and do it. Who would like to try it? Basically, I want to know what's the mutual information between this column and this column. You're right. Go ahead.
Yeah, I can do it. Okay, so we need the different probabilities for A being in the first position, for A being in the second position, and the same for you. Sorry if you can't read my writing. And then the jump probabilities for each combination. So AU, AA, UA, and EU. So these. And we can simply count, so we have for A in the first position we have 3 out of 4, so it should be 5. In the second position we have only 1 out of 4. And for you it's the other way around. So in the first position we only have 1 out of 4. And in the second we have 3 out of 4. And for each combination we can see we don't have AA and we don't have UU, so we have 0 for these two, and we have 3 pairs of AU, so again 75%, and 1 UA. Okay, and then we only have to use the formula, so and calculate it like for each of the pairs. So yeah, let's say 1 is always X and the second position is always Y. So we have, for example, for AU, we have probability of AU, so 7 times logarithm of 0.75 divided by the probability of A in the first position and U in the second. So you have 5. And then for the other pairs, you can skip AA and UU because it's 0, and if we multiply with 0, it remains 0. So the only other pair is UA. So we have 0.25 times the logarithm, and now this time everything, all the probabilities are 1/4. So it's 5 divided by. no idea what
Yeah, so
comes
it's
out, but I think all together was 0.81.
yeah, sounds right. And that's last question. What units is this? I don't think I asked that in the quiz.
Bits.
Bits, exactly. Bits. Because this is log 2. It turns out if you can use the natural, yeah, thank you. It turns out you can use the natural log and it just changes the units to nats. But bits is so much nicer, so much more intuitive. Yes, thank you. So basically you're saying that that there's basically one bit of information being shared across these guys. And actually, there's a way you could have increased that, or did I say 1 bit? I mean, slightly less than 1 bit. And you could have actually gotten, this number would have been higher if we had this, right? Because there's actually, if you look at this column, how much information is in this column? So the simple way to look at this is just say, okay, these are exactly distributed 50-50, and so how many bits of information do I need to tell you? So like if I flip a coin, to tell you what is head or tails?
2. Or 1.
Somebody said 1. Why?
Because you have two possibilities, and if it is like 0 or 1.
Yes. So in this case, so I mean technically, the amount of information that I give you, or the amount of information that's in this variable is 0.5 log base 2 of 0.5. Right. This is let's say the probability of A plus 0.5 log of 0.5. Where this 0.5 is the probability of U. Confirm for me that adds up to 1. Actually, I think we want minus here. Can somebody confirm that this adds up to 1?
Yeah.
Yes. Okay. So how much information an observation gives us depends on the probability of that event, event happening, right? And so here we had a slightly different situation where it's A more often than it's U. So U gives us a lot more information. Like U would give us log base 2 of 0.25, but it happens infrequently. Most often it's A. So basically this column is giving us like 0.25 log base 2 of 0.25 plus 0.25 log base 2 of 0.75. Sorry, I meant 0.75. So it turns out that this sum gives us slightly less than this sum. This is going to give us exactly 0.81. Because in this case we have perfect communication between the channels. Yeah, I think that's the same number. Yeah. Sure. So the mutual information has to be at most the information in whichever column has least information. You can't share more information than you actually have. Right. So that's kind of like, it's kind of like this. You have a certain amount of information in your channel X and a certain amount of information in your channel Y, and this is your mutual information shared between X and Y. Right. So this thing can never be bigger than X, nor can it ever be bigger than Y. Okay. And it turns out you can apply this to this problem of coevolution between sequence positions. You can also use it to things like, for example, like evaluate the quality of your cryo density matrix right? And you can see, like, you can say, oh, I've managed to fit this DNA into this blobby density here, and I'm not sure if it's significant because the resolution is so low, right? So what I do is I calculate the mutual information between my molecular model I put in there and the density map. And it turns out that this is a much better measure than many others you could try. Anyway, so that's about all that I want to tell you today. Well, last year we had a lot more slides, but it's a lot of it is redundant information. I think this captures the gist of it, so I think it's enough. Are there any questions? Questions? Okay. Then I believe next time is not me. What's next lecture? Anyway, I'll see you next time.